Okay, so let us continue with trying to classify Riemann surfaces. So you see we have already looked at two cases when the universal covering of a Riemann surface is P1, the Riemann sphere, then we have seen that the Riemann surface itself has to be P1, that is holomorphically isomorphic to P1, which is C union infinity, okay, via this stereographic projection. And we have also seen that if a Riemann surface has universal cover the complex plane, then its fundamental group has to be abelian, and there are only three cases: the fundamental group being 0, in which case it is biholomorphic to the complex plane, then the fundamental group is being Z, isomorphic to Z, the integers under addition, in which case it is a Riemann surface structure on a cylinder, on a real cylinder, and the standard covering map in this case is just the exponential map from C to C star. The punctured C star is a punctured complex plane, okay, and C to C star is the exponential map. So this is the single representative, okay, and when the fundamental group is isomorphic to Z cross Z, then the Riemann surface is a complex torus, okay. So these were the cases when the universal covering was the complex plane. Now we have to look at those Riemann surfaces with universal covering the upper half plane, okay, which is the only case that is left, and of course instead of the upper half plane we can also choose the unit disk, okay, because they are biholomorphic to one another, and I will only begin with trying to look at those Riemann surfaces which have universal covering the upper half plane and which are abelian, okay. So in this way I would have covered classifying all Riemann surfaces which have abelian fundamental groups, okay. So fine, so how does one proceed? So one needs to somehow try to answer the following question: what are the kinds of Mobius transformations that you can find in the deck transformation group, okay. So that is a question that needs to be answered, right. So let me write that down. See, you know that X is a Riemann surface with let me say universal covering X sub univ. So you have this universal covering, okay. Then you know that if I fix a point small x in capital X, then the first fundamental group of the base based at the point small x is naturally identified with the deck transformation group of this universal cover, okay, which is a subgroup of holomorphic automorphisms of the universal cover, okay. So and of course the universal cover modulo this deck transformation group is precisely X, okay. So the question is what are the elements here, okay. So you know so this has only three possibilities, you know, X sub univ is a Riemann surface and it is a simply connected Riemann surface. So this is either P1 which is a Riemann sphere, or it is a complex plane, or it is the upper half plane, okay. And in each of these cases the group of holomorphic automorphisms are Mobius transformations. Okay, so automorphisms, the holomorphic automorphisms of P1 are going to be all Mobius transformations. Okay, these are all Mobius transformations, and then you have the automorphisms of the holomorphic automorphisms of the complex plane are going to be just the upper triangular ones. Okay, and the holomorphic automorphisms of the upper half plane are going to be with real coefficients. Okay, so but these are all of course these two are subgroups of this, and they are all in any case they are Mobius transformations, and the question we have to ask is what is the image of the fundamental group here. Okay, the question we want to ask is what is the image of the fundamental group here. In other words, we want to know which among these holomorphic automorphisms, namely which among these Mobius transformations are going to be in the deck transformation group. Okay, that is the question. So we need to somehow study them in a little bit more detail before we can cover the case when the universal cover is the upper half plane. Okay, so let me recall what we do is that a Mobius transformation is it going to A z plus b by c z plus d where AD minus BC is not 0. Okay, this Mobius transformation is identified with an element of PSL2C. Okay, namely the normalization that one does is that one makes the determinant equal to 1. Okay, so can be normalized to satisfy determinant is equal so I should write determinant of the matrix to satisfy AD minus BC is equal to 1. Okay, so what I mean by that is you can so what I mean by that is I mean that's how we wrote the you know the groups these groups. So what we did was we took so for example you take this Mobius transformation so this is z going to A z plus b by c z plus d, and I am going to just map it to the following element of PSL2C. Okay, namely I will put A B C D. Okay, and let me call this as capital A. Alright, I will call this as capital A, and what I will do is the determinant of this is now AD minus BC. Alright, but I would like to have the determinant to be 1. So what I do is I divide by determinant square root of determinant of A. Okay, so what I do is I map this to the element. So if I call this as A, so let me write it properly. So I will map it to 1 by root of AD minus BC times this. Okay, so what I mean is so here this AD minus BC equal to 1 is a condition. Of course if AD minus BC is not 1, then I will have to change this ABCD. Okay, and how I change it is by dividing through it by square root of AD minus BC. because you see now the determinant of this is going to be, you see it is going to be square of this, okay, which is 1 by AD minus BC into determinant of this which is AD minus BC, so it is determinant 1, right. And of course I have put a P here, which means that I am not worried about plus or I am not worried about the other representative which is putting minus everywhere, okay. So these two representatives are supposed to form one class, okay, because this is just SL2C, the determinant 1 matrices, okay, 2 by 2 matrices modulo the subgroup given by plus or minus the identity, okay, that is what PSL2C is. So let me write that down, this is just SL2C determinant 1 modulo the subgroup given by plus or minus identity, that is a 2 by 2 identity matrix, okay. So this is how you identify Mobius transformations with elements of PSL2C, and it happens that this is a the Mobius transformations here on this side, this is a group under composition, and this is also a group under multiplication, standard matrix multiplication, and this map is a group isomorphism, okay, this map is an isomorphism of groups, okay. So that is how you identify all the Mobius transformations, a group of all Mobius transformations with the with PSL2C, okay. And of course the group of all Mobius transformations is exactly the set of all possible holomorphic automorphisms of the Riemann sphere, okay, right. So all biholomorphic maps of the Riemann sphere onto itself, which you can also think of as biholomorphic maps of C union infinity, the point at infinity onto C union infinity, all possible biholomorphic maps, they are given exactly by these kind of Mobius transformations, which are also called sometimes as linear fractional transformations, also as bilinear transformations in some books, okay. And the way you identify these Mobius transformations with PSL2C is in that way, okay. Now of course when I say those Mobius transformations which preserves the complex plane, they are going to be this subgroup, and this subgroup corresponds to putting C equal to 0, okay. You put C equal to 0, you will get the upper triangular form, okay. And those Mobius transformations which preserve the upper half plane, okay, the set of complex numbers with imaginary part greater than 0, okay, the upper half plane, then these Mobius transformations are going to be exactly these elements with A, B, C and D real numbers, okay. You will get real numbers because if a Mobius transformation preserves the upper half plane, okay, then it will also preserve the boundary of the upper half plane. The boundary of the upper half plane is the real line, okay. So the real line is just thought of as a real axis, okay, and you know, if a Mobius transformation preserves a domain, it will also preserve the boundary of the domain, okay, and it will also preserve the exterior of the boundary of that domain, right. So what will happen is that this Mobius, if you have a Mobius transformation that preserves the upper half plane, then it has to preserve, it has to map the real line onto itself, okay, and that condition will tell you that all the entries have to be real numbers, okay, it will tell you that all the entries have to be real numbers. So you can check that, right, fine. So now the question is, these are the kind of objects, these are the Mobius transformations that are going to come up here, alright, and I want to know which of them are going to be coming from the fundamental group, namely which of them are going to be deck transformations for a covering, okay. Now obviously this has to have to do with certain intrinsic properties of Mobius transformations, and how we get these properties is by considering two kinds of ideas. One is the fact that so one is based on the number of fixed points of the Mobius transformation, okay, and the other thing, the other idea that helps us to classify Mobius transformations is looking at this this matrix representative, okay, and looking at its trace, okay, and the trace is, you know, as you know, is just the sum of the diagonal elements, right. So what I am going to do is I am going to say the following things. So first let me make the following definition. So classification of Mobius transformations can be done based on two viewpoints. A, the number of fixed points, number of distinct fixed points, or let me just say the number of fixed points, let me not even say distinct. And B, the trace of a matrix representing the transformation, okay. So the classification is done on two viewpoints. So let me so first of all let us look at fixed points, okay, let us look at fixed points. So first of all, notice if I look at a Mobius transformation and try to study the fixed points, I will get at most two fixed points, okay. That is because I will be solving AZ plus B by CZ plus D equal to Z, okay, and that at worst is going to give me in general it is going to give me a quadratic equation in Z, and it will have two roots, alright. Of course if C is 0 I will not get a quadratic equation, right. So so note that there can be at most two fixed points for a non-trivial Mobius transformation, okay. There can be at most two fixed points for a non-trivial Mobius transformation, okay. In fact if you find a Mobius transformation fixes 3 points or more, then it has to be the identity transformation. I mean that is what this means, okay. That is because again as I told you, you will at the most get a quadratic in Z that you have to solve for by equating Z to AZ plus B by CZ plus D, okay. Now what we do is we look at the case when the Mobius transformation has exactly one fixed point, okay, and we call the Mobius transformation as parabolic, okay. So so definition, a Mobius transformation is called parabolic if it has only one fixed point, okay. a Mobius transformation is called parabolic if it has only one fixed point, right. Now what are the kind of Mobius transformations that you can think of which have only one fixed point, okay. You can obviously see that, you know, if I take a translation z going to z plus b, okay, then that translation will have only one fixed point, namely the point at infinity, okay. So obvious examples, translations z going to z plus a, let me put z going to z plus beta, are certainly parabolic, since of course, you know, beta should not be 0, right, because I do not want the identity map, I am not looking at the identity transformation, okay. Beta is not equal to 0, okay, with infinity as the only fixed point, okay, infinity is the only fixed point. Now the question is, as I told you, the other viewpoint of looking at a Mobius transformation is by looking at the trace of a matrix that represents the transformation. So if I take this matrix, so what I do is I look at the matrix of this, the matrix representing it is, well, it is 1 beta 0 1, okay. The matrix that represents this is 1 beta 0 1, and of course this is determinant 1, this is determinant 1, and if I want to consider it as an element of PSL2C, I have another choice, namely I can put -1 minus beta 0 minus 1, okay. There are two representatives, because if you go modulo plus or minus identity, so this has two representatives here, right. So let me write that, or -1 minus beta 0 minus 1 in SL2C. These are two representatives I can get in SL2C, okay. Now well, of course, you know, if I take trace, okay, the trace is, in this case the trace is going to be 2, trace is sum of the diagonal elements, so trace is 2, okay, and in this case the trace is -2, okay. You can always see that if I take an element of PSL, okay, PSL2C, if I take a representative in SL2C I will get two representatives, okay, and both the representatives, the only difference will be all entries will differ in sign, okay. Therefore what will happen is that when you take the trace will also change by sign, okay. So in order to make this ambiguity disappear, instead of considering the trace we will consider the square of the trace, okay. So consider trace square, okay. So if I take trace squared, you will see that trace squared of 1 beta 0 1 is 2, and that is also is equal to 4, and that is also equal to trace squared of the other representative. If I take -1 minus beta 0 minus 1, both of them have trace squared 4, okay. And now it is amazing that these two properties actually characterize parabolic, this property characterizes a parabolic Mobius transformation, namely you take a Mobius transformation, okay, it need not directly look like a translation, okay, but if you know it is parabolic, okay, then its trace will be 4, okay, and if the trace is 4 then it will be parabolic, okay. So it is this property of the trace squared, so the trace squared being 4 characterizes a parabolic transformation, okay, trace squared being 4 characterizes a parabolic transformation, right. So let me write this lemma, a Mobius transformation is parabolic if and only if given a representative so let me write a representative in the form A B C D in SL2C, which means AD minus BC is 1, okay. Trace squared ABCD, that is A plus D the whole squared, is actually equal to 4, okay. So in other words, the property of the Mobius transformation having only one fixed point, okay, is captured by the fact that you take a representative matrix, okay, in SL2, then trace squared is 4, okay. Of course again you know the trace squared is important because if I had taken the other representative, the trace would have, the other representative will be minus A minus B minus C minus D, alright, and the trace of that will be minus A minus of A plus D, okay. So just to eliminate that sign we take trace squared, and the trace squared equal to 4 is the condition for Mobius transformation to be parabolic, okay. So this can be kind of proved in a nice way, and of course let me also add one more lemma. We have seen that translations are certainly parabolic, okay. So the converse is also true in the following sense: you take a parabolic Mobius transformation, then you can conjugate it by some suitable Mobius transformation, so that the resulting transformation is a translation, okay. So let me write that lemma: a Mobius transformation is parabolic if and only if it is conjugate by a Mobius transformation, by a suitable Mobius transformation, to a translation, okay. So please try to understand the following: we have defined a Mobius transformation to be parabolic if it has only one fixed point, alright, and then we saw that translations are standard examples of parabolic Mobius transformations, and you take a translation and you calculate its trace squared, you take a translation, take a representative matrix, calculate trace squared, you get 4, okay. Now the trace squared being 4 for a general Mobius transformation with a matrix representative forces conversely that the Mobius transformation has to be parabolic, namely that it has only one fixed point, okay. Also translations are examples of parabolic Mobius transformations, and what this lemma says, conversely you take a parabolic Mobius transformation, you can conjugate it by a Mobius transformation, okay, and you will get a translation, okay. So what does this mean? This means the following. So what this means if Z going to AZ plus B by CZ plus D is parabolic, then and only then we can we find a Mobius transformation alpha beta gamma delta with alpha beta gamma delta and this Mobius transformation A B C D, then multiplied by alpha beta gamma delta inverse. So this is conjugating the matrix representing this Mobius transformation by another Mobius transformation, okay. This is equal to a translation, so it should be of the form 1 0 1 beta. Let me put something else here, so put T here, okay. So of course AD minus BC is 1 and alpha delta minus beta gamma is also 1. So these are all Mobius transformations, these are all representatives in SL2C, okay, determinant 1, okay. So you see actually see it's very easy to see more or less that these lemmas are they are easily provable. So for example let me explain. Suppose I have a Mobius transformation which is so suppose you grant me the first lemma, suppose you assume the first lemma is true, okay, then the second lemma can be reduced from the first, okay, because you see if a Mobius transformation is parabolic, okay, then it is by the previous lemma its trace squared is 4, okay, and I claim that if trace squared is 4 you can actually solve for alpha beta gamma delta so that you get a transformation like this with, for example, even with t equal to 1, okay. So and the so let me write that down, okay. So proof, so let me number these lemmas, let me call this as lemma 1, let me call this as lemma 2, okay. So well, proof of lemma 1, you see so you know the condition is for the Mobius transformation to be parabolic it has to have only one fixed point, okay. So the condition is that AZ plus B by CZ plus D equal to Z has only one solution, okay. When you say it has only one fixed point then this equation should have only one solution, okay. So this means let us write this down, so maybe I should write here if Z going to AZ plus B by CZ plus D is parabolic, then this has only one solution, that is, let me cross multiply this, I will get Az plus B is equal to Cz squared plus Bz has only one solution. Has only one solution, okay, and if I rewrite it, I will get Cz squared plus d minus a into z minus b equal to 0, okay, has only one solution. Okay, so that is so when will that happen? There are two cases we can consider, the case when C is 0 and when C is not 0. If C is 0, okay, then it will happen, okay. If C is 0, okay, notice if C is 0 then AD is 1 because AD minus BC is 1. If C is 0, AD is 1. So in particular D minus A cannot be 0, okay. If D minus A is 0, okay, then you will get yeah, so let us look at this. If C is 0, AD is 1, in fact I think yeah, if C is 0, AD is 1, D minus A is not 0, then Z equal to B by D minus A is the unique fixed point. Okay, the other possibility is D is equal to A, okay. If D is equal to A, okay, then what happens is, so you say C is 0, D is equal to A, then the transformation becomes is Z going to, you see it is going to be A Z plus B by C is 0, so 0 Z plus D is just A, so I will get Z plus B by A, okay, and this is a translation, this is a translation and it has only one fixed point, namely the point at infinity, okay, is a translation with infinity as the unique fixed point. Okay, so this disposes of the case when C equal to 0, okay. If C is not 0, what happens? So let me go over here and continue. If C is not equal to 0, okay, we want the quadratic CZ squared plus it was D minus A into Z minus B equal to 0, okay. You want only one solution, okay, you want only one solution, you want only one fixed point, okay. That means this quadratic equation should have equal roots, okay, okay, to have equal roots, okay, which happens if the discriminant is 0, so I will get D minus A the whole squared minus 4 into C into minus B is 0, okay. So the condition becomes D minus A the whole squared plus 4 BC is equal to 0, okay. If I expand it I will get D squared plus A squared minus 2AD plus 4 BC is 0, okay. But you see AD minus BC is equal to 1, okay. So I will replace this, I will get AD minus 1 is equal to BC, so 4AD minus 4 is equal to 4 BC. So if I put it back here I will get D squared plus A squared minus 2AD plus 4AD minus 4 is 0, and this will come to A plus D the whole squared is equal to 4. Okay, so you will get trace squared ABCD is equal to 4. Okay, so you see, if C is not equal to 0, then we get trace squared equal to 4. Alright, so I will have to go back and look at these two cases and look at whether I can conclude whether trace squared is equal to 4. So the first thing I want to say is, you see, in the case C equal to 0, okay, this is the unique fixed point, and when I say is the unique fixed point, it is the unique fixed point in the complex plane. Okay, so there is actually one more fixed point, and that fixed point is the point at infinity. Okay, and therefore this case cannot occur because we have assumed that it is parabolic. So I just want to emphasize the following thing, namely when I say look at the number of fixed points, I mean in the extended complex plane. Okay, it is important that you also look at whether infinity is a fixed point or not, okay, which is exactly happening, for example, in the case of a translation. In the case of a translation, the unique fixed point is a point at infinity. Okay, so you also have to look at whether infinity is a fixed point, and if C is 0, okay, then the transformation becomes Z going to A Z plus B by D. Okay, and for that infinity is a fixed point. Also the point at infinity is also a fixed point. So you get two fixed points in C union infinity. Okay, one a finite complex number which is a fixed point, the other one is a point at infinity. So you get two fixed points, and therefore C equal to, the case C equal to 0, D the case C is equal to 0, D not equal to A, okay, cannot occur. Okay, so in that case we do not have anything to prove. Alright, so let me write that down. So let me write that here. The case C equal to 0, D not equal to A gives two fixed points, so does not occur. Okay, and what about the other remaining case? The other remaining case is when C is 0 and D is equal to A. Okay, then in that case you can calculate the trace squared is actually 4. If C is equal to 0 and D is equal to A, okay, then you know AD equal to 1 will imply that A squared is 1. Okay, so trace squared ABCD is going to be A plus D the whole squared, that is 4A squared, it is A plus A the whole squared, it is 2A whole squared, so it is 4A squared, but you know A squared is 1, so this is equal to 4, so you will get trace squared equal to 4. So what we have established is that if you start with a parabolic transformation, okay, which is by definition a Mobius transformation having only one fixed point in the extended complex plane, then trace squared has to be 4. Alright, and let us prove the converse. Okay, that is also quite easy to see. Conversely, if trace squared ABCD, which is A plus D the whole squared, is equal to 4, okay, suppose this is the case, again we look at the cases when C is 0 or C is not equal to 0. If C is not equal to 0, then we are in this situation, okay, and you can actually reverse this argument, and you will get that this quadratic equation has discriminant 0, and therefore there is only one root, okay, and therefore you will get that it is parabolic. Alright, and notice that if so I will have to look at the situation when C is equal to 0, okay, and the case when C is equal to 0, okay, there are two cases. I will show that A equal to D will occur, alright, and A not equal to D will not occur, okay. So let me write that down. If C is not equal to 0, then C z squared plus D minus A z plus minus B equal to 0 has 0 discriminant and hence a unique solution, okay, and of course in this case you must remember that infinity cannot be a solution for this, because you have C z squared plus D minus A into Z is equal to B, okay. If I push the B to the other side, if I substitute infinity on this side, since C is not 0, I will get infinity on this side, on the other side I will have B, and B cannot be equal to infinity, it is a finite complex. A, B, C, D are of course finite complex numbers, so in this case you will not get infinity as a fixed point, there is no chance. So this is something that you should always keep doing, you must check whether by any chance infinity is becoming a fixed point, okay. So so if C is not equal to 0, then this has 0 discriminant and hence a unique solution. So the Mobius transformation is parabolic, well if C equal to 0, we will have if C is equal to 0 you will have AD equal to 1, also you will have A minus D the whole squared is A plus D the whole squared minus 4 AD, okay, and that will be but you know A plus D the whole squared is given as 4, so I will get 4 minus 4 which is 0, okay, and this will tell you that A is equal to D, alright, and so if A is equal to 0 D, then the transformation becomes Z going to A Z plus B by 0 Z plus A, which is just Z plus B by A, and this has only infinity as the unique fixed point and therefore is parabolic, which is parabolic, it is a translation. So of course when C is 0, the case A not equal to D, that does not occur, just like we saw here, okay. So this proves lemma 1, alright, okay. So let me now try to give you a proof of lemma 2, which is quite simple. So proof of lemma 2, okay. So there is a very easy case, namely if you are able to find a Mobius transformation such that when you conjugate this ABCD by this Mobius transformation you get a translation, suppose you are able to find one, okay, then you know if I take trace on both sides, okay, you know trace is invariant under conjugation, therefore if I compute the trace on the left side I will simply get trace of the matrix in the middle, okay, and therefore it is going to be just A plus D the whole square, okay. On the other hand here if I compute the trace I get 4, okay. So if this holds then it is clear that the Mobius transformation has trace squared equal to 4 and by lemma 1 it has to be parabolic, okay. So let me write that, let me call this equation as star, okay, I am calling this equation as star, okay. Clearly if star holds we get trace of A plus D the whole squared trace not of A plus B the whole trace squared ABCD is equal to A plus D the whole squared is equal to trace squared of 1 0 1 and T, which is 4, okay. So by lemma 1 the given the Mobius transformation is it going to AZ plus B by CZ plus D is parabolic, okay. Conversely, assume that it is parabolic, okay. Conversely, assume Z going to AZ plus B by CZ plus D is parabolic. We can try to solve for alpha, beta, gamma, delta complex numbers so that star holds say T say with T equal to 1, okay. So you write star as you see alpha, beta, gamma, delta into ABCD is equal to 1 1 0 1 into alpha, beta, gamma, delta. I am just multiplying on the right by alpha, beta, gamma, delta, okay. We get 4 equations in alpha, beta, gamma, delta, okay, which are homogeneous with determinant matrix with coefficient matrix so the coefficient matrix, if you write it down, you will get a 4 by 4 coefficient matrix having determinant and guess what the determinant is? The determinant is A plus D the whole squared minus 2, okay. So it is no, it is A plus D minus 2 the whole squared, sorry, it is A plus D minus 2 the whole squared, okay. And you see which is not 0, not equal to 0 by lemma 1, okay. Oh sorry, which is equal to 0 by lemma 1, sorry, which is equal to 0, okay. See, because we have assumed this is parabolic, lemma 1 says that trace squared is 4, okay. So trace is plus or minus 2, alright. Now if trace is 2 then this is 0, okay. If trace is minus 2 you can solve for the same system by replacing A, B, C, D with minus A, minus B, minus C, minus D, in which case you will get a minus here, okay. So if trace squared is 4 I can really solve for this, alright, and I will get a non-trivial solution, and therefore I can find a Mobius transformation like this. I leave it to you to check that you can also make sure that the non-trivial solution satisfies determinant 1, okay. So I leave that as an exercise. So that proves that lemma 2 is true, okay. So if you want to solve a homogeneous system and you want a non-trivial solution, then the coefficient matrix has to have determinant 0, and the point is the determinant has this, it is connected with the trace, that is the whole point. Okay. So okay. So I will stop here. Okay, we will continue later.